Welcome to the next lecture of General Relativity. I'm your host, Rifat Bari, graduate student of physics at Brown University. Today, we're going to be talking more about basis transformations. We have two coordinate bases. Let's say we are starting with the Cartesian basis, and we want to translate that to the polar basis E sub r and E sub theta. The question is, how do we implement that transformation? The answer to that question, the Jacobian, right? So we can write E sub r, we can express E sub r as a linear combination of some amount of the E sub x vector and some amount of the E sub y vector. Similarly, we can express E sub theta as some amount of the E sub x vector and some amount of the E sub y vector. Now here's the magic idea. In the previous lecture, we figured out that basis vectors are the same as partial derivatives in tensor calculus. In other words, we figured out that, let's hit the board here, E sub x is the same thing as the partial derivative of some position vector r with respect to the x direction. Similarly, E sub y is the same thing as the derivative of a position vector in the y direction. And we can do the same thing. We can write the basis vectors for E sub r and E sub theta in a similar manner. We can say that they're partial capital R, partial R, and partial theta, partial R, partial theta. So this is the big idea, that basis vectors can be rewritten as partial derivatives. Now, why is that helpful for us? Well, we can rewrite these basis vectors now as partial R, partial X, and partial R, partial Y. If we do that, then we notice something amazing. And what is that? We notice that this equation is nothing more than the multivariable chain rule. How so? Let's hit the board over here. What we're trying to figure out is what linear combination of E sub x and E sub y is going to deliver E sub r, for instance. Well, let's take the yellow chalk here. E sub x can be rewritten as the derivative of the position vector with respect to the x direction. And similarly, we can do the same thing for E sub y. And so now the question is E sub r, which can be written as partial r, what is the linear combination of these two basis vectors that gives us E sub r? Well, the answer is delivered to us by the multivariable chain rule. Let's grab some colored chalks. So this is simply partial x, partial r, and this is partial y, partial r. Why so? Well, check it out. Partial x, I'm not really allowed to do this, but hey, on camera, I can do it. Partial r, partial r, partial r, partial r, that gives me the full derivative, dr. And so that's why the Jacobian J, the Jacobian matrix, is made out of these partial derivatives. These partial derivatives are partial x, partial r, partial, so that I get the actual Jacobian, not its transpose. So what you're saying is something like that. All right. So now let me show you a concrete example of how to switch between Cartesian and polar coordinates. So Cartesian and polar coordinates. All right. So in the Cartesian basis, in the Cartesian coordinate system, I have two basis vectors. First of all, I have an x coordinate and y coordinate, and I have an E sub x, also known as I hat, and I have an E sub y, also known as j hat. Now, in Cartesian coordinates, I have something wonderful. And what is that wonderful thing? That wonderful thing is that if I move around in my coordinate plane, my basis vectors don't change in magnitude or direction. If I move over here, look, E sub x stays the same length, E sub y stays the same length. Bada bing, bada boom, everything is nice and simple. But you can't take that for granted, because in the polar coordinate system, things are not so easy. In the polar coordinate system, we have two basis vectors once again. We have the E sub r vector, which is radially outwards. So let's say I'm at this point. E sub r would be radially outwards like this. And we have the E sub theta vector, which is tangential to one of my polar circles. The thing is that these basis vectors don't stay the same when I move around in the coordinate plane, right? For example, if I move over here to this circle, E sub r is no longer to the downwards direction. Now it's going to be upwards. This is E sub r. So its direction changed. And E sub theta its direction is not only going to change, its magnitude also changes. In this video, we're using, once again, the non-normalized definition of E sub theta. In some textbooks, they define E sub theta as partial r, partial theta, followed by a normalization factor of 1 over r. Here we're choosing not to opt for that because we just want these derivatives. We just want E sub theta expressed in terms of these partial derivatives. Okay, so the moral of the story is that in Cartesian coordinates, we're taking something for granted, which is the consistency of the magnitude and direction of our coordinate basis vectors. Whereas in polar coordinates, our basis vectors can change not only direction, but also magnitude, right? So now here is the question. Here is the question. Let's say that I start with a point in the Cartesian coordinate plane. Let's make it simple, like 1, 1. What is that same point in the polar coordinate system? Well, that's pretty simple. You say, I know the transformation from Cartesian to polar is x is r cosine theta, y is r sine theta, and likewise r is x squared plus y squared, and theta is arctan of y over x. So I have all the transformation rules between the two coordinate systems, so I can plug that in. So if x is 1 and y is 1, then I know that r is square root of 1 squared plus 1 squared, which is square root of 2, and theta is arctan of 1 over 1, which is pi over 4. Bada bing, bada boom, I now have my point converted from Cartesian to polar coordinates. So let's write 1, 1 in polar coordinates. It's going to be the square root of 2, so it's going to be somewhere between r is 1 and r is 2. So let's say this is r is 2, and it's going to be at an angle of pi over 4. So pi over 4 is about this. So let's say that this is our new point, square root of 2, comma pi over 4. So this is our point. This is the exact same point in two different coordinate systems, in the Cartesian and in the polar coordinate system. But hang on, that's not what we're going for. We're trying to figure out how our basis vectors change, not how our coordinates change. Coordinates change all the time. They're not anything that's manifestly physical. Okay, so how do we figure out how our basis vectors change? Well, for that, we need to turn to our Jacobian matrix. So let's create our Jacobian matrix for the polar coordinate system. The elements of my Jacobian are the partial derivatives of partial x partial r and partial x partial theta, and similarly partial y partial r and partial y partial theta. Now let's just evaluate these partial derivatives for our coordinate system here. So here is x is r cosine theta. So if I derivative that with respect to r, that becomes cosine theta. Similarly, derivating y in terms of r gives me sine theta. Derivating x in terms of theta gives me minus r sine theta. And derivating y in terms of theta gives me r cosine theta. Now, once again, I've written theta not in the normalized fashion as some textbooks do. I just want to emphasize that here, the chain rule says that the partial derivatives are just simply our basis vector. So that's why I've written it the way I have. Now, we can simplify this even further, not really simplify it, but make it notationally simpler. Cosine theta is the same thing as x divided by r. Similarly, sine theta is the same thing as y divided by r. Minus r sine theta is the same thing as minus y, and r cosine theta is the same thing as x. So here is our very simple Jacobian for the transformation of basis vectors from Cartesian to polar coordinates. So now let's plug in our numbers. Here we have the point 1, 1. So, and these are the basis vectors e sub x and e sub y in the Cartesian coordinate frame. So let's plug that in over here into this matrix and see what we get for our polar coordinate frame. Remember that our x and y coordinates in Cartesian was 1, 1, and our r value was the square root of 1 squared plus 1 squared, which is the square root of 2. So now let's plug that in here and let's see what we get for our Jacobian. So our Jacobian is going to be, so x divided by r, okay, so 1 divided by the square root of 2. Likewise, y over r, 1 divided by the square root of 2, minus y, that's going to be minus 1, and x, that's just 1. So, ladies and gentlemen, this is my Jacobian matrix for this problem. Now, how do I figure out my new basis vectors? E sub r and e sub theta at a given point are equal to the Jacobian times our original basis vectors, e sub x and e sub y. That means that e sub r is simply equal to 1 over the square root of 2 e sub x plus 1 over the square root of 2 e sub y. Similarly, e sub theta is equal to minus 1 e sub x plus 1 e sub y. So great. So we've got our two new basis vectors. So now we can just draw it. So it seems that e sub r is going to be halfway in both directions. So this is going to be e sub r here. This is my e sub r vector here. Okay, and e sub theta is going to be minus 1 in the x direction, so minus 1 in the x, and 1 in the y. So here's e sub theta. Wow, look how amazing that looks. Look how clinical this looks, right? You can see that the theta basis vector is tangential to my r equals square root of 2 circle, and the radial vector is literally just radially outward. So it cannot get better than this, folks. So now what we're going to do is talk about the anti-Jacobian, or as I like to call it, the inverse Jacobian. So let's hit the board with that. So the inverse Jacobian, the Jacobian takes us between the polar coordinate system and the Cartesian coordinate system. What if we wanted to go the other way?
Can't we just use the inverse matrix formula?
Absolutely. Well, actually, so it turns out the math gets really nasty that way, because for a 4x4 matrix, for a 2x2 matrix, the Jacobian is, in our case,
it's a 2x2.
partial, right, partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta. Now we could just find the inverse by doing 1 over AD minus BC. And do you remember how to find the inverse of a matrix? That's 2 by 2?
You negative these two and then you swap the other two.
Okay, so minus partial x, partial r, minus partial y, partial theta, partial y, partial r, partial y, partial theta. Okay, so now here is where the math gets a little messed up, because these are partial derivatives, and doing this with them is not exactly the same as doing AD minus BC with just simple scalars. So we've got to figure out another way to find the inverse. Can we think of a better way? Aha! We can just use partial derivatives as the basis vectors. So here's what I mean. Now we want to express e sub x and e sub y, our Cartesian coordinate basis vectors, as a linear combination of e sub r and e sub theta. So now, how do we figure this out? Well, simple, you say. All we have to do is rewrite e sub r as a partial derivative of the position vector r with respect to r. Similarly, e sub theta is partial r, partial theta. And we're going to repeat that over here. Partial r, partial theta. And so now all we have to do is use the multivariable chain rule. Remember, e sub x is nothing but partial r, partial x. Similarly, e sub y is partial r, partial y. And so the multivariable chain rule calls us, demands that if I want to get partial x on the bottom here, I just have to multiply this fraction by partial r, partial x. Similarly, I have to multiply this fraction by partial theta, partial x.
Hey, it should be partial, oh yeah.
Similarly, I have to multiply this vector by partial x, partial r, partial y, because I want to get y on the bottom, and partial theta, partial y. So check it out, bada bing, bada boom, I got my anti-Jacobian very simply. My inverse Jacobian is simply partial r, partial x, partial theta, partial x, partial r, partial y, partial theta, partial y.
Interesting.
Now you might say, wait a second. How do I know you're just not fooling me? How do I know that this is really the inverse of the Jacobian? Bada bing, bada boom, multiply them together. And what do we expect if we multiply them together?
Identity.
The identity. Let us see if that is indeed what we get. Now, let's go ahead and demonstrate that multiplying the Jacobian and anti-Jacobian does indeed produce the identity. So what I'm going to do is multiply partial x, partial r, partial y, partial r, partial x, partial theta. Say it with me, partial y, partial theta. Coding scheme, partial r, partial x, partial theta, partial x, partial r, partial y, partial theta, partial y. All right, let's go ahead and multiply these two together. Let's see what we get. So we're going to take this row, multiply it by this column. So I just want to make sure that's clear for the viewers. So let me highlight that out. I'm going to multiply this row by this column. So we're going to get, so partial x partial r times partial r partial x. And let's use a neutral color for the summation. And partial x partial theta and partial theta partial x. All right, so our first summation is done. We now move on to the second column. This is our second column. This was the first. So we now have partial x partial theta partial theta times partial r partial y. Partial r partial y. Now, immediately I can sense that something is wrong because something's not adding up here. They should be canceling out. So I have partial x partial r, you see. There should be an r vector here. Times partial theta partial y. Partial x partial theta times partial theta partial y. Start with partial y partial r multiplied by partial r partial x plus partial y partial theta multiplied by partial theta partial x. And let me implement a subdivisional chamber between rows and columns.
Is this a subtraction mechanism?
And finally, we implement the final row slash column of our matrix, which is partial y partial r, y partial theta, partial y partial theta times partial theta partial y.
Solving this one is an exercise left to the reader.
Now, dear viewer, this might look a bit foreign, but let's say we have a function f which depends on two variables r and theta, which both depend on x. How can we figure out how f depends on x? In other words, what is df dx? Well, that would simply be partial f partial r partial x plus partial f partial theta partial x.
Bullshit alert.
Now, Shimo, I'm going to have to edit this if you do that. Then you have to do it again, bro. So now if f is just a function x, then check it out. What do we have here? If not, partial x, which is just 1, partial x, which is just 1. This is just the whole derivative of x with respect to itself, which is just 1.
But wait, that's the exact same thing as what we see in this upper quadrant.
Exactly. This entire upper quadrant is just 1 written in a fancy way. This is just 1.
And the same thing holds if we just plug in y here, right?
Well, if we plug in dy dx,
Not dy dx, it's dy dy, dumb.
Dy dy. But first let me explain dy dx, which is just 0, because y has no dependence on x. But as our viewer suggested, dy dy is also 1, which makes this column, this entry of our matrix 1. And this entry of our matrix is 0, because partial y partial x is 0. Similarly, partial x partial y is 0. That leaves us with nothing but the famous identity matrix. So now, if we wanted to express this in a simpler notation, here's what we could do. Let's denote our x coordinate as c1 and our y coordinate as c2, c for Cartesian, and 1 for the first Cartesian variable.
Yeah, we're not stupid.
Similarly, P1 for r and P2 for theta. Then I can rewrite this entire matrix in the following notation. Instead of writing all of this commotive mess, I can write, instead of partial x partial r, I can write partial c1 partial p1.
How does this make it any
And
better?
instead of partial r partial x, I can write partial p1 partial c1. And similarly, I can do that for all the entries of our matrix. So you might say this is not helping, but this entire matrix can now be rewritten in terms of Einstein summation notation, very simply as follows. We can now write partial c sub I, partial p sub j, partial p sub j, partial c sub k. This does not necessarily have to be the same index as this, because as you can see, sometimes we have an x here, but a y down here.
And this is equal to jij.
And this is actually equal to the Kronecker delta. Why? Because the Kronecker delta is nothing but the identity matrix in component form. And so the moral of today's story is that we can use these partial derivatives to really do the hard work for us. That cuts out our hard work. And so now you can see just how simplified the mathematics becomes. Thank you for watching this episode of General Relativity. I hope you enjoyed learning with me.